All right. Hello. It's Monday in Boone. I'm making the recording here is to be played on Monday. I'm hoping you can get it then, but you can use it throughout the week. I'll get the results of your test back. The plan is to get it back to you before the week's over. And like I've said before in class, give me a week on getting the grading back. There's a lot of stuff going on here. The online stuff is taking time and it's taking a variety of different life circumstances. It got some challenges coming with it and stuff. So just be patient, please. I'll get you exams back soon. Later this week is the plan, okay? But for right now, what I want to do is I want to move into talking about chapter 5. It has to do with antiderivatives and things of that nature. But what I'm wanting to do is antiderivatives, section 4.8, the last section in chapter 4, is talking about, it's called antiderivatives and differential equations. And I just want to say something briefly about antiderivatives, and maybe a little different than the way they formally do it, but I want to just get across what the idea of an antiderivative is, if you haven't thought about it before. And antiderivative is the opposite of derivative, you know? So it's kind of like a definition they're going to give in the situation that I'm going to show you that they use in the text has to do with cap F, an uppercase F and a lowercase f. And the lowercase f is the original function, and the cap F is considered the antiderivative. So the question you have to ask yourself each time when you first get in the hang of this, is if you're told little f of x is 6, what did I have to take the derivative of to get 6? All right. So the idea is, what did I have to take the derivative of to get 6? And the first thing that comes to mind, I know, think it yourself, but 6x comes to mind, right? And so the derivative of 6x is 6. That's the idea. And you're going the opposite direction. So you're going from here to here. All right. So it's a matter of recognizing, where did this come from? When I took a derivative, it got me to 6. What did I start with is the question. Okay, so that is the idea of antiderivative. The opposite direction is derivative. Another one I want to talk about is this. Like if you have 2x for f of x, what did you take the derivative to get 2x? What did you take the derivative of to get 2x? I hope you recognize, remember, bring the exponent down front and subtract 1. Therefore, that must be x squared, yeah? That's what it came from. So the antiderivative of 2x, an antiderivative of 2x is x squared. Now, one of the other situations you've got to be conscious of with this now, it's pretty straightforward. You know, if you look at 2x squared, bring the 2 down front, subtract 1, you get 2x, right? That's the answer. So the antiderivative of 2x, an antiderivative is x squared. Now, well, there's another answer that comes up with, there's another antiderivative of 2x. One other thing you consider of, let's see, if you have 2x for your answer, the point I'm making is cap f of x could also have had something added to it, like this, right? Well, what's the derivative of this? This is cap f. And the derivative of 3 is 0. So the derivative of this is also 2x. All right? So we've got a situation where there are multiple possibilities where this came from. Both of these go to 2x. X squared plus 3, x squared. If that 3 was a million, the derivative would be 2x. If it's square root of 3, if it's negative 5, whatever it is, if it's a constant, you take the derivative, you get 0. So the notation we're going to use from now on, and I'm going to ask you to make sure you use it. It's a critical part of making a correct answer now to certain types of questions. But if you're asked for what are all the solutions for what's the antiderivative of 2x, the main idea is that we use the letter C. So you get x squared, and so cap f of x would be equal to x squared plus some constant. you take the derivative of this function, and that's a constant c. You take the derivative of this, you get 2x, no matter what that c is. So this is a generality about a general solution for the antiderivative type moment, okay? Now, one other thing I want to point to is, yeah, so the C is an important part of that situation. One other thing I want to point to is this. Hang on a second. So if you look at, let's do a couple other examples. If it says find all the derivatives for x, f of x equals 0, okay, so stop and think. What do I take the derivative of and get 0? Okay, if I take the derivative of 5, like we were saying a minute ago, a million, any constant. So the answer to this question would be the fact that, you know, you could use the notation cap f of x would be equal to any constant. Any constant, you take the derivative of it, you get that. And we'll use the notation of antiderivative in just a little bit. Right now, we're just getting the concept of antiderivative going, okay? And so now look at this. Look at this next one down here, the g of theta. G of theta equals negative sine theta. Okay, what do you take the derivative of to get negative sine? Right, you with me? Positive cos. So if we had a cap g of x would be equal to cos theta. And again, if there was some constant added to it, that derivative would be 0. So you need the plus c in order to get that final answer. That's all the general solution to this. Some c can be added onto that. Now, one that's a little more challenging is this one. The next one is this one, h of x equals x to the 1/2. So, and again, you got to stop and think now, when you took the derivative, you got 1/2 as an exponent. So where did that come from? You know, you had to subtract 1 when you took the derivative to get this. So that means you have to add 1, or you have to add 2/2 to that 1/2. And that's going to end up what, giving you 3/2, right? So it ends up being that it's going to be x to the 3/2. But notice this also, if you take the derivative of this, when you take the derivative of this over here, that you got to bring that 3/2 down front, right? So that means, and all I have here is 1. So that means I must have had in front of this something to cancel out that 3/2 when I brought it down, make it 1. And the reciprocal of 3/2, if you notice, is equal to 2/3. All right? So now look at this. If I take the derivative of this, bring down the 3/2 down here, multiply it times 2/3, that's equal to 1, right? And I raise and then I got to subtract 1 on the power, and that gives me the 1/2 that is right there in that situation, all right? So, and again, if you had any constant added to that, that would be part of the solution as well. If you're asked for all antiderivatives that was given up in the initial problem. Okay, so that is that situation. Now, tell you what, so it's a matter of, you got to stop and think when you're doing antiderivatives. You got to get the rules down. There's some specific rules I want to point to in just a second here. Matter of fact, let's go there now. I'm going to point out the, let me change where the stop share and go to the text. I've got a table of functions here. If you notice this, the rules, you can keep coming back to this when you're looking at other problems. You know, so the idea of a constant, derivative of a constant is 0. Derivative of cos was negative sine. We got all these different rules. Well, the situation of, look at x. Look at that second one up there, up there, the f of x equals x plus a constant. That would be, you take the derivative of x, what do you get? 1, right? And the constant is 0. So you end up with f of x equals to 1. Now, if there was another constant of some kind, like if it was 5x, then the derivative of that would be 5, and the constant goes away, etc. But look at the general rule now for the third one down. If you've got x to the a on the left-hand side over here, if you've got x to the a over here, all right, then the derivative, remember what we got to do, the power needs to be 1 more than that. So you add 1 to that up there, and then in the process of doing the problem, you got to divide by that new exponent. You got to divide by that new exponent. So I'm going to go back to that problem we just did a second ago, and let you see again that on the iPad, that when we had that, the initial problem here was down here is what I'm talking about. If I have h of x equals 2/3 x to the 3/2 plus some constant, this 5 will be good for right now. Now I'm gonna, if I take the derivative of this, look what has to happen here. The derivative is I bring the 3/2 down front and multiply by that 3/2, right? So when I go back the other direction, when I got x to the 1/2, notice what's going to happen here. I've got to add 1, and so I'm going to divide by that same power that we built up here. Okay, so the idea is that if I have x to the 3/2 here, and when I multiply by that, by the coefficient here, I get 1. Well, that's, and notice that if I'm going the other direction, I've got to divide by that the new exponent that I came down and multiplied by the front. So the idea is, the rule is, if you look back at the rule, if I take the antiderivative of this, cap h of x has got to be equal to, I've got to add 1 to the exponent up top, and then I've got to divide by the new exponent that I get up here. Divide by the 3/2, and that results in multiplying by 2/3. You flip and multiply. So what you do is you raise the power and then divide by that new power. Okay? And let's do another example in just a second here. Let me show you this one. Tell you what, let's go to a new one. All right. Here's one I'd like, and let's go back to the idea of when we had f of x equals x squared. All right. The rule we said a second ago, the idea is the derivative of that would be 2x, right? But what's the antiderivative of this? This had to come from, we must have taken the derivative, we had to subtract 1 from the exponent, so it must have been 3, right? And the situation is, so cap f of x has to be equal to x to the, I add 1 to the exponent, and then the main idea is that means there is no value in front, so the 3 that I get, I've got to divide by that new exponent that I just added, okay? So I have to divide by that 3. So I divide by the 2 plus 1. And we'll go back to the formula in just a second. So the answer to this ends up being x to the 3rd over 3, or 1/3 x to the 3rd. So the antiderivative of x squared is you add 1 to the exponent and divide by that new exponent, okay? That's the key idea. And so let's go back to when we started with 2x. If we had f of x equals 2x, let's find out what cap f is, all right? That means we got to raise the power by 1 and divide by that new power. So I end up with 2 to the x, this was 1, so I've got to add 1 to that, 1 plus 1, and I've got to divide by that 2, right? And that means the 2's will cancel, and I end up with cap f of x equals x squared. The 2's cancel, and I've got to remember to keep that plus c going, because we've got that plus c needs to happen when you do the antiderivative. So you end up with x squared plus c. Now, you go back, take the derivative of this. Do you get 2x? Absolutely. So you raise the power by 1, divide by that new power, and add the c on there when you're doing a general answer on that kind of line, right? So let's go back to the rules that I was just pointing to. All right. So notice that third one down, when you've got f of x equals x to the a, when you've got f of x equals x to the a, the antiderivative of it is x to the a plus 1, and you divide by that new power, a plus 1, and then add the c. All right? So, and there's a couple other basic ones that we've got there that the e to the x is a straightforward one. If you notice that one down here, e to the x, what's the derivative of e to the x? What's e to the x? So what's the antiderivative? E to the x plus c. You got to make sure you just remember to add the c. You get the same thing back. Notice natural log of x. Notice what's the derivative of natural log? Remember, the derivative of natural log is 1 over x. We end up with 1 over x, okay? So the antiderivative of 1 over x is going to take you back up to the natural log function. And notice that there's absolute value signs around that x. That's a crucial part of the answer, plus c. So the derivative, and notice it's x to the negative 1 is another way to write 1 over x. The antiderivative of 1 over x is natural log of x, absolute value of x, plus c. All right, we'll talk about the others. And notice down here, sine and cosine. Derivative of sine gives you cos. So the antiderivative of cos is sine. And the derivative of cos is negative sine, right? So in order to get positive sine, you must have started with negative cos. So the antiderivative of sine is negative cos. You got to get that into your head. Remember, the derivative of sine is cos. Therefore, the antiderivative of cos is sine. It gets you back to sine. But then the situation of the derivative of sine is cos. The antiderivative of cos, therefore, is sine. That takes a little practice. It'll be something you need to get squared away. We'll talk more about this in a little bit. I want to now move into another problem I'm going to ask you to do. It's got differential equations in the differential equations, solving equations of that sort. So tell you what, let me go back to, I want to show you the a slide that comes from the one of the slides. I've got 4.8 slides here that shows on the in sapling. So notice what's happening here. The section 4.8 antiderivatives. The spelling, make sure you're comfortable with it. Find antiderivatives. Solve a differential equation. We're going to do those two things. I'm going to do that next in just a minute. But the whole thing I've been talking about right now is antiderivatives. We'll get into the notation for that a little bit later. Section 5.1 has really hit that strongly. But get the concept of it. It came from 4.8. And now let's solve a differential equation. I want to show you that in just a second. And a little bit, I'll move on to a different recording. Okay? So see you in a minute. Okay, tell you what, before we do the differential equation, let's do one more practice problem having to do with antiderivatives, all right? Let's do this. This one's got 3 terms to it. I'm going to show you the one that I've got going here. It's going to be on my iPad. And it's got 3 terms, and there are slightly variations on the theme. Stop and think about things. Recognize, we're going to take the antiderivative of these 3 terms. And the circumstance is there's a verification in the section that talks about the fact the sum of antiderivatives is equal to the antiderivative, no, excuse me, the antiderivative of a sum is equal to the sum of the antiderivatives. Just like with, with derivatives, it's the same situation. We got the same thing going here. So we're going to need to take the antiderivative of each of these terms and getting the solution. And notice in the instructions, it also says find all antiderivatives. All means therefore it's an antiderivative. I'm going to need to remind myself that I've got a plus c. I got to make sure I keep that. That's part of a correct answer on this one. So let me just talk about this now. The antiderivative of each of these terms. All right. The antiderivative of e to the x, remember what it is? Yes, it is very straightforward. It's just like the other circumstance. It is e to the x, okay? But it's plus c. Now, I'm going to make a little notation that every one of these antiderivatives has a different constant, okay? So, but if there, we got three of them are gonna happen. So we're gonna end up at the end putting a general plus C at the end, but it's gonna be made up of one that comes from each of these different antiderivatives. So I'm gonna call this first one plus C1. You don't have to do this every time, but I'm gonna get the concept across. The final C we're gonna put on this thing is gonna be made up of C1 plus C2 plus C3, all right? Now let's take a look at this next one. We got 6 over x to the second. What's another way to write that? 6 over x to the second. Let's bring that x squared up top. That means we've got 6 to the negative 2. All right? So if we've got to take the antiderivative of this term, what we got to do is raise the power by 1 and divide by that new power. Yeah? So if this was what we might call g of x, then cap g of x, the antiderivative would be raise the power by 1 and divide by that new power. That's negative 2 plus 1 is negative 1, so I'm dividing by negative 2 plus 1. Let's just write that down, just like it is, which is equal to 6x to the negative 1 over negative 1. That negative 1 hits the 6. That is equal to negative 6, and that's just going to be over x. So notice this. Notice what we started with. That's x to the 1 power down there. You don't have to write the 1, but notice what we started with. It was x to the negative 2. We're taking the antiderivative. So that means we're going to add 1 to the exponent. We've got a negative 2, add 1 to it, it becomes negative 1. And that, as a result, takes us back to the denominator. It's just a 1. So the answer to that function right there is actually you get a minus sign, but the 6 stays, but it becomes minus because the negative exponent and the exponent drops by 1 right there. You know what I'm saying? All right. And remember that if we were doing this separately on its own, then that would be plus a constant. All right. Every time you do this, you don't have to do C1, C2, C3. Just put a C on at the end. It's totally fine. But I want you to remember, every time you do one of these, this could be plus 5. This could be plus 7. You know, this C1 could be plus 5. This could be plus square root of 2 or whatever. Now the last one. What antiderivative of negative sign? Saying, what did you take the derivative of to get negative sign? Yes, it's cos. So we end up with plus cos x plus c, and I'm going to call this one plus c3. These three are different constants, right? So what we could say at the end, though, is we end up with this, and this, plus some constant where, and you don't have to make note of this, but where c is equal to c1 plus c2 plus c3. That's going to be something I just want you to make sure you understand that concept, that that the situation is that every one of these antiderivatives that were needed gave you an additional C, C1, C2, and C3. So when you finish the problem, you just got to make sure you stick a C on it at the end. But it's really made up of these three additions that came together, the sum of those three terms, okay? So when you're doing a problem yourself, if you're dealing with this problem right here, what you could come up with, if this is it, this is the problem that you've got to work with right there, all right? Then you could immediately go to cap f of x is equal to e to the x minus 6 over x plus cosine x plus c, knowing that that c is made up of something here, here, and here. Those three things added together, okay? So that is, I wanted to make sure we covered that before I hit the differential equations. Back in a flash. Okay, one last thing from section 4.8 has to do with what are called differential equations. And in different sciences, for instance, in physical science, chemicals, chemistry, biology, other circumstances, scientists use mathematical laws that describe and predict certain types of behavior, right? And these laws often involve the derivatives of an unknown function. So in other words, they're able to determine that they've got the derivative of some function. And it's a matter of figuring out what function did this come from, you know? So for instance, here's a situation that we're contending with right here. Let me show it on my iPad. If you've got this function right here, this is a derivative function. And we needed to determine what function did it come from, okay? So this is the form of a differential equation. dy dx equals some function. And then figuring out what y is, where it came from, is using a differential equation to come up with a function that describes the data, okay? So one type of answer is a general equation which will have a c in it when we take the antiderivative and stick a c on the end. And let's do that now. We can solve this problem in that direction. So what do? We go to each term and figure out what the antiderivative of each term is. So what we're going to be doing, this up here is actually the derivative. So what we're trying to find is what is y, right? We're finding out the original function. And where did it come from? What did we take the derivative of here? What did we take the derivative of to get 5x squared? Raise the power by 1 and divide by that new power. The 5 is there, x to the second. I raise that to 1 by 1 power and divide by that new power. All right? Great. Now, what next? What did I take the derivative of to get 2 for my answer? Yes, 2x. That's exactly correct. All right? And this is, the question was, find a general solution, which means what could be possibly a variety of things we're uncertain about, including that constant that's being added at the end. A general solution is this. You take the derivative of this function, you get this, no matter what that c is, okay? That is what's called the general solution. Well, if you're going for a particular solution, if you want a more specific answer, then you need one more piece of information. And what they call it in this text is, the authors call it a boundary condition. So for this problem, they're saying it uses differential equation, what we're given here. Let's do that again. I'm going to write that down here, but this time I'll also include, there is one value that you're given for one of the coordinates of a point on the answer that you're looking for. And so a boundary condition, it's called. A boundary condition is that x equals 3 when y equals 5. All right, and that can be given as the coordinates of a point too, if you're given, but the way they give it in the text is this, they give this as well. And now, so the situation, if you're given this problem, here's a differential equation, you've got the boundary condition, then what you got to do is go in and figure out the general solution and then plug in the y and the x and see what c, figure out what c is. And then rewrite it with c in place of the new value in place of c. So in other words, if you're given this question right here, this one instead, okay, do the antiderivative. Okay, well that means y equals 5x to the third over 3 plus 2x plus c. All right, now I utilize this information right here, plug 5 in for y, and 3 in wherever all the x's are, and solve for c. So I end up with 5 equals 5, 3 to the third over 3 plus 2 times 3 plus c. We don't know what c is. We're trying to figure it out. All right, so that ends up giving us 5 equals 5. One of these 3's cancel. Therefore, that cancels with one of those. And that makes it 9. 5 times 9 plus 6 plus c. That's 45 plus 6. 5 equals 51 plus c. Therefore, subtract 51 from each side, and I get c equals negative 46. Therefore, now I plug this back into here, into our solution that we got, And that final answer, the particular solution, is going to be this. I plug it back into the original answer that I got, the general solution, but I stick in the minus 46 and verify that that's the solution. And now there's two things that should be true. When I take the derivative of this function, I get our differential equation, okay? And I do. We need that negative 46 becomes 0 when I take the derivative. I get 5x squared plus 2. That matches this right there. But also, when I plug in 3 and 5 into our final equation, it's a true statement. So when I plug in 3, I get 5/3 27 plus 6 minus 46. So that ends up being minus 40. 3 goes into there 9 times. I got 45 minus 40 equals 5. Checks. That's exactly correct. And also when I take the derivative of this, I get dy dx equals 5x squared plus 2. So that checks and this checks, therefore I have solved the differential equation appropriately. Okay, I'll do one more example and then I'll let you get on to your problems, all right? So let me solve one more problem here. I'll be right back. Okay, so let's do this one other problem and then you get going and hitting those problems. There's 22 of them in section 4.8 and I encourage you to get started on it right away. Get as many done because we're going to be moving on through this week. The quiz on Thursday is going to include section 4.8 and 5.1 questions, all right? So right now I want to look at this other problem here. I'm giving you a differential equation with a boundary condition. So I'm giving you that dy dx equals x squared plus 2x plus 1 with the boundary condition that when x equals 3, then y equals negative 1. And then to verify the solution, that's saying show that the derivative really comes to that and show that when you plug the numbers in, our new answer does work. So first thing we got to do is take the antiderivative of those three terms, right? So y is equal to x squared. I raise the power by 1 and divide by that new power. Raise the power by 1. I'm going to write this out again. You don't have to do that every time. You're done with it. That's cool. Okay, plus 2 times x to the 1 raised the power by 1, divide by that new power. And then plus 1, it's a constant. Therefore, what did I take the derivative to get 1? I took the derivative of x, all right? And then you've also got plus c, because it's asking for, you first find the general solution, and then solving for c will get us solved for c using the boundary condition, okay? So let's do this again. What do we get here? That's x to the 3rd over 3. The 2's cancel, so I get plus x squared plus x plus c, right? That's y. And now I plug in the boundary condition. I'm going to solve for c now. This is the general solution. If you're asked for a general solution, that's the answer right there. Now, apply the boundary condition and solve the specific solution. So at x equals 3, y equals negative 1. Y equals negative 1. X equals 3 cubed, 3 squared, plus 3, plus c. So I end up with negative 1 equals, one of those 3's cancel. So I get 9 plus 3 plus c. I end up with negative 1 equals 18 plus 3 is 21 plus c. Therefore, subtract 21, c equals negative 21. Therefore, my final equation is y equals x to the 3rd over 3 plus x squared plus x minus 21, excuse me. No, it should be 22, right? You subtract 21 and you end up with minus 22. So that is minus 22. And that is the correct answer. All right, so I hope you see that. Now the idea is verify that situation. So it says to verify the solution. So first, what is dy dx equal to? Okay, if I go up here, what's dy dx? dy dx, take the derivative of each term. I bring the 3 down front, subtract 1 on the exponent, bring the 2 down front, subtract 1 on the exponent. Derivative of x is 1 minus 0, which gives us 1, right, this is 3 on the bottom. The 3's cancel, and I end up with x squared plus 2x plus 1. That is dy dx, and that confirms the thing that we started with up top here. And now I'll confirm also our boundary solution makes the 3 and negative 1 should be a true statement. So I end up with negative 1 equals, so I'm plugging 3 and negative 1 into here. 3, negative 1 into there. Plug in negative 1, I get negative 1 equals 27 over 3 plus 9 plus 3 minus 22. I get minus 1 equals 9 plus 12 minus 22. 21 minus 22 is minus 1. Check. This checks and this checks. I verified the solution. It is done. All right, thank you. And now, next thing, that's it for today. Hit the 4.8 problems, practice them, get them down. Again, there's 22 of them. Some of them are really short. Some of them are a little more convoluted. Take your time, get it down, and come in with questions. Let me know what's going on, all right? Be well.